Very excited to be talking for Brew Ed CLE tonight. I was just telling Louise actually that one of the reasons why I'm really excited about talking to you this evening is that I wholeheartedly credit Brew Ed Cleethorpes for sort of setting me on this journey of learning about lots of things to do with cognitive science and curriculum and sequencing, because I attended the conference January last year, just before the pandemic started. So thank you very much to Louise and the whole team there that organised that, and this evening as well, and all the other talks that we've had since. So I'm going to talk to you this evening about sequencing in action. It's very much going to be based on my experience as a teacher, as a science teacher. And so I'm hoping that, obviously, I'm hoping all the scientists amongst you find something really useful in this. And even if you're not a scientist, I'm hoping that the principles that I talk through might still be applicable to your subjects. But science is very much my specialism, so I'm going to stick with what I know. So you can find me on Twitter at Mrs._McGhie. And I have just recently started blogging. There aren't very many posts on there yet, but if you fancy reading the ones that I have written, it's paperpensandpedagogy.com. So I am a science director with Outward Grange Academies Trust. And I've been working as a science director for 5 years now. And before that, so I started teaching in 2016 in London. I was there for 5 years and moved up to York. And I actually did 2 head of science roles before starting as a science director. So I'm really privileged in my current role that I get to work with and support science departments across our trust. I'm usually deployed to a couple of academies and I work really, really closely with the teachers there. Doing CPD and training and drop-ins and supporting them, but also supporting the heads of departments and developing them, but also very much teaching year 11s as well. My focus is year 11s and outcomes. And so I'll work with either groups of students or whole classes if I need to. So some of the examples that I'm going to use this evening are actually very recent ones that I've developed during this year with the year 11s that I've been teaching. I also coordinate for the trust the CPD for all of our science teachers across the trust and deliver quite a lot of that myself as well. So this is something I really love doing. And this year in particular, since January, I've been working with a subgroup of my colleagues on our Key Stage 3 sequencing. And so it's something that I will get to in the second half of this talk. So what is sequencing? I went to the Oxford Dictionary website and grabbed their definition. So sequencing is the process of arranging things into a particular order. And then just for a bit of variety, I went to the Cambridge Dictionary and theirs was very slightly different. And I found this quite interesting. So the Cambridge Dictionary definition is that it's the process of combining things in a particular order. And that idea of it's not just putting things into a certain order, but it's combining them in an order. I thought was a nice little addition and that I will use as well when I give you one of my examples. So why do I think that sequencing is so important, and why does thinking about sequencing help? So I, as I said, work with year 11s quite a lot. And usually the reason why I'm working with these year 11s is that they are not achieving very well in science. So my remit will be to work with, let's say, I had a group of 12 this year. They higher combined students, but who were just really not getting their heads around chemistry at all, and just they hadn't achieved very well in their mocks, and they just had the mentality of, well, they just can't do science. But they were very bright students and they were very clearly higher combined students. They just needed that extra support to get there. So because I tend to work with students like that, who, in a sense, I think need to be turned around quite quickly, if that isn't a harsh way to talk about students, but they need something different. They need a type of input that is going to make them get it quickly, because usually in year 11 we're on a limited time frame, so that they've got their GCSEs at the end of the year, pandemic notwithstanding. And so they need something that's going to accelerate their progress. So So I think very carefully. I think a lot about what I teach them, the order that I'm going to teach it, how I'm going to deliver it, sequence it in a way that's going to really make them understand it fundamentally. And I like this analogy of hooks. And again, for me, in my head, this just helps me to understand this concept, that anything that's new, any new learning, really needs to be hooked onto current learning that's in their head, so current knowledge that's in their head. So this new knowledge is more securely remembered when there is prior knowledge already there that you can hook it onto. So if your coat hooks are really secure on the wall, then you're going to be able to hang your coats and your bags on it really easily. But if that prior knowledge isn't secure, so if those coat hooks are wobbly, they've not been screwed into that plank carefully enough, then those coats and bags are liable to drop off. Equally, I like this analogy because you can keep going, can't you? If that wall behind the coat hook starts to crumble, then those coat hooks are going to drop, and all the coats and bags are going to drop as well. So that's very much the starting point for me, is before I teach them this concept that they need to learn, that they did possibly, badly on their mocks in, what are the fundamental concepts before that underpin that they haven't got? So the example from this year 11 group I was teaching chemistry to this year is we started with, they had to do organic chemistry. But in order to understand organic chemistry, alkanes and alkenes, etc., fractional distillation, they needed first to have a really strong understanding of covalent bonding. And in order to have a good understanding of that, ultimately, I went right down to the structure of the atom and how the periodic table is structured as well, and before trying to teach them about fractional distillation. So I went right back with them because they didn't have those initial concepts, those initial foundational ideas secure in their minds yet. So if we think of all new learning as needing to be hooked onto prior learning, this ties in really nicely with everything that we know from cognitive science, and I love reading sort of all the books on cognitive science I can, and the blogs, etc., because to me it just fundamentally makes sense, and the fact that it's obviously research based as well is great. And so I'm always thinking, how can we apply these principles to our teaching? And so if we have isolated bits of knowledge, isolated facts, they're actually really difficult to remember long term. And I think that instinctively we know that. If you can connect those facts to each other somehow, then they become much easier to remember. But if you can connect them to the knowledge that students already have in their heads, so there's my own diagram of students' mental schema in their heads. So if we can make those connections, then again, that knowledge is likely to be remembered longer term. It's going to be a lot more secure. And then obviously you want to reinforce those connections over time, etc. So I know that when we think about mental schema and how knowledge is remembered over time, it isn't linear. Okay, so these mental schema are almost like complex webs, aren't they, of bits of knowledge that are attached together, and we end up grouping them into these schema, so they're chunked. So it's not linear, but speech and writing are linear. When we talk to students, it's linear. When they read a bit of text, it's linear. And so the sequencing and the clarity of what we say to students or what they read is really important. So we can think about sequencing at different levels. We can think about it between units and also within units. And I think that there are always, we'll know in our subjects, there are always concepts that are more difficult than others. So for example, you wouldn't teach bonding before students had an understanding of compounds, for example, or an understanding of atoms, for example. So that there's clear sequencing when you look at a big scale, certain topics that you just wouldn't teach before they'd done other topics. You can also think of sequencing in terms of what happens in a lesson, so the sequence in your lesson. So that essentially is the structure of your lesson. So it's things like your starter, where you're checking prior knowledge, the teacher exposition element of the lessons, where the teacher's explaining a new concept, checking for understanding, faded practice, and then independent practice. And obviously smattered throughout there, you've got your feedback and questioning, etc. And we tend to be I won't say we tend to be good. I think we've got a lot better actually at this checking prior knowledge and prior understanding as part of our starter before we go on to explaining the new thinking, the new concept. But I think sometimes we actually don't link well enough students' prior learning to the new learning. We assume that students are able to do that for themselves. So this connection here, we've checked their prior knowledge, they're secure, that's great. But then this connection here between the prior knowledge and the new content to deliver, I do think that as teachers and experts in our subject, we sometimes overestimate how quickly students are going to be able to make those links for themselves, because they are usually novices, obviously, novice learners in our subject, whereas we are expert learners. So our mental processes will be much faster when it comes to making the connections between prior learning and the new content being taught. So I think that that's one area that we can do better on. And then the other one is just that sequencing through the new content that's being delivered. So what I want to focus on first is not sequencing between units or sequencing within a unit, but actually sequencing at the level of your explanation. So we need to consider not just what the student knows, their prior knowledge, but also in what order we're going to present new information to try and maximize their understanding of that new information and therefore their longer term retention. So I'm going to give you an example. So this is one, again, that I taught this year to this group. So reaction profiles in chemistry. And if we think of the prior learning required, it would be reactants and products and an understanding of chemical reactions. We might expect them to have an understanding of making bonds and breaking bonds, and the fact that when bonds are broken, the chemicals take in energy. When bonds are made, they release energy. Endothermic and exothermic reactions, so reactions that either give out heat or take in heat energy. And then possibly activation energies as well, so the minimum amount of energy required to start a reaction. So that's great. Our students have got this prior knowledge. We've checked it. We're happy they're secure. And then very often what happens is we'll go from that to, okay, so today we're going to learn about something called reaction profiles. And here is an example of a reaction profile. And it might not be labeled straight away. You might label it with them. So I'm going to, at this point, switch. And hopefully you can all see that now to my visualizer. And so we might even not give them one that's already printed, but we might draw one live for them. So we've got here the reaction, so proceeding, and then here we've got energy, and we start off with the energy of the reactants, and the energy increases, and then it decreases, and then we end up with the energy of the products. So then we might start to label it, and you might actually label your different parts like this, which is a tip that I learned this year actually reading someone's blog. I forget which one, apologies. But this way, you can talk about the different parts of the graph much more easily. Sorry, that's not a straight line. That annoys me. And so you'd say, right, so from A to B, what we've got there is the energy of the reactants. From B to C, the energy of the chemicals or the reactants is increasing. And so this here, between B and C, is your activation energy. And then from C to D, their energy, the energy of the chemicals, is decreasing. So they're giving out that energy. And then you end up with the energy in the products. And so you can compare the levels of energy, etc. So to me, and I think to many teachers, this sounds like a perfectly logical sequence. But when I was thinking about this a bit more, particularly with this group who were just really struggling to get their heads around this, I thought, well, actually, I think I'm doing this backwards. Because when I explain it like this, as I've just demonstrated, what I do is, so talk about what happens between A and B, talk about what happens between B and C, so energy increasing, and then I'll go, well, why is that? Why does the energy increase between B and C? And it's because they are having to take in energy because bonds are being broken. So if the reactants are taking in energy in order to break the bonds, then their energy levels are increasing. Okay. And so it ended up, what I found was that I was going, well, B and C energy levels increase. Why? Because they're taking in energy. Why? Because you're breaking the bonds. Why are they having to break the bonds? Because that's how you're then going to rearrange the atoms to make your products. And so essentially, what I think I was doing is talking about the finished product, the last thing actually in a sequence of processes, because something before that would happen, because something before that would happen, because something before that would happen, etc. And it just occurred to me that it's essentially like telling a story backwards. And then I thought, well, you wouldn't do that, would you? You wouldn't tell a story backwards. You wouldn't tell the story of Goldilocks by saying, well, at the end of the story, Goldilocks jumped out the window. And the reason why she did that is because she'd woken up with 3 bears standing around her bed, looking at her really cross. So she was scared. And the reason why that happened is because the bears had come back from their walk to find that someone had broken into their house. And the reason why she was in that bed was because she was really tired. And the reason why, etc., etc. So stories don't work that way. And I know that our students need to learn how to describe graphs, and they need to learn how to interpret graphs, and they need to learn how to explain those graphs. But when they're first encountering those graphs in that context, so like the example of reaction profiles, I just flipped it round and I just started at what I considered to be the very beginning, rather than starting with the graph and working my way backwards. So if I show you what I mean by that, I've lost my rubber. Here we go. So what I did instead is I started with the reaction. So if we just take methane, just a nice simple reaction, methane burns in oxygen to form carbon dioxide and water. And I left the balancing of it initially, but I said, okay, well, what does this reaction actually mean? So we've got 1 carbon here and 4 hydrogens. And then we've got our 2 oxygens here. And this is how I did it for them. So I'm going to try and do it a bit quicker for you. So then we've got 1 carbon in our carbon dioxide and 2 oxygens. And then I'm trying to get my colors right. We've got an oxygen, which I've done in green. There, oxygen atom there, and 2 hydrogens. Okay, so then I use this as an opportunity to revise a little bit of balancing equations with them. I said, well, these, right, so what's what? So we just recalled that these were our reactants. And then carbon dioxide and water are our products. Okay, so then these atoms that are in the products, where did they come from? They come from the reactants. Okay, so how many have I got here? I've only got 1 oxygen atom there, but I started with 2. Well, that's not possible. So we quickly balance this together. There we are, we're balanced. Okay, are we? Oh no, see, right. So this is where I should have had my see, all the scientists now watching this are shouting at me going, that's not right, Christina. Let me try that again. This is where I should have had my crib sheet next to me, because I forgot the 2 oxygen atoms here. So we're back to 1 oxygen atom there, 2 hydrogen atoms, which I've done in blue. Okay, great, right. So let me start that again. We've got 2 oxygen atoms here. We've got 3 oxygen atoms here. Well, that's not going to work. And we've got 2 hydrogen atoms here, 4 hydrogen atoms there. So I was going right. See, this is what nerves do to you. So we've got 4 hydrogens there now and 2 oxygen atoms, but we've also got these 2 oxygen atoms here. So actually it's 4 in our product. So we need another 2 in our reactants. Okay, great. So we're now balanced. And we can write that here and here. Okay, so we've now got the right number of atoms. Right, so in this reaction, what is actually happening to the atoms? And you get to the stage where students can say, well, they're just being rearranged. Okay, so in order for that to happen, what has to happen to the atoms first? Well, they need to break apart. So these bonds in the reactants that are holding the atoms together need to be broken. So we want to end up with all of these atoms separate, 1, 2, 3, 4, and 1, 2, 3, 4 oxygen ones. Excuse the fact that they are not the same size. So what happens is the atoms first break, and then the bonds between the atoms break, which, by the way, requires energy. So energy is taken in. Energy is taken in. And then once all those bonds have broken, so bonds broken, energy is taken in, then they're going to reform. So when they reform, the opposite is going to happen. So bonds are made and energy is given out. I can't spell this today. Energy is given out. Okay. So we started back at first principles, and I haven't even touched on reaction profiles yet. So bonds were broken first, and that energy was taken in. By the way, remember we've learned this before. This is called your activation energy, which is the minimum energy required to start a reaction. And the reason why that energy is required to start the reaction is that it breaks all of the bonds in the molecules first, and then the atoms are free to rearrange themselves to make these new bonds. And when those new bonds are made, that energy is given out. So then it's okay, well, let's think about the energy. So as the reaction is happening, if we think about the energy in the products, and I construct the diagram with the students rather than giving them one first and then trying to explain it to them or get them to explain it to me. So I say, okay, well, let's start with the energy levels of our reactants here. And because we've actually got named reactants now, instead of writing reactants, I'm going to actually write the formulae for the reactants balanced. So tell me, guys, my students, what is it that happens first? And we've just talked about it, so they can tell me, well, the first thing that has to happen, what is the first step in a reaction? The first thing that has to happen is all of those bonds have to be broken. Okay, so in order for that to happen, what do the substances, what the chemicals have to take in? Well, they have to take in energy, miss. Yes. So if they're taking in energy, what is happening to the amount of energy in those chemicals? Well, obviously it's going up. Right. So how am I going to show this in my graph? Well, the line's going to go up. Okay, great. So the line goes up. And this here, this increase, what's that called again? The amount of energy required to start the reaction that breaks all of those bonds initially? That's the activation energy. So because we've done it in this order and we've done all of this preamble first, it's the students are actually telling me what the reaction profile is going to look like rather than me showing them an example and then trying to break it down. So I say, okay, well, what's the next step now? So we've broken the bonds by taking energy in. What's going to happen next? Well, new bonds are going to be made. Great. So what does that mean in terms of energy? Well, they're going to give out energy. Okay, so if these chemicals are giving out energy to the surroundings, what's happening to their levels of energy? Well, they're going to go down. And if they go down to this point, now we write our products, if they go down to this level here, so these are our products, these are our reactants here, do the products have more or less energy than reactants? Well, they obviously have less, because the students now understand this diagram, because this graph, because instead of them just being shown it and me talking through it with them or trying to get them to explain it, they have constructed it verbally themselves based on their prior knowledge that we have really carefully sequenced. So now we can start to link it to things like exothermic, endothermic reactions. So, right, so in this example, the chemicals have given out more energy than they have taken in. So overall, have they given out energy or taken in energy? Well, they've given it out, right? Remember we did this last lesson. What's it called when you have a reaction that gives out energy? Well, that's exothermic. Excellent. So this is the reaction profile for an exothermic reaction. And what I found was with these students, they understood that so much better and they remembered it so much better long term as well, that way around. And it was a bit of a light bulb moment for me. And it's how I will forevermore teach reaction profiles. So it was about not telling the story backwards and starting from the genuine beginning. So what if you've got a subject or a concept that you want to teach where there isn't a genuine beginning like that? So it might be, for example, the carbon cycle. So there's no beginning to the carbon cycle because it's a cycle. So again, we check for prior knowledge. We're looking at things like photosynthesis, respiration, combustion, fossil fuels, possibly decomposition. And at this point, we've checked all that prior knowledge. Excellent, students have got that spot on. And then very often we'll throw up this diagram and we'll talk it through or get students to explain to us what's happening. And I think that's cognitive overload. We've checked all the prior knowledge, but what we haven't done is then carefully sequence from that prior knowledge to this concept that we're trying to teach them. We've just thrown them in at the deep end. So the alternative is actually drawing the diagram. But even then, again, in the last year or two, have changed how I sequence, how I draw that diagram. So typically, I always started with carbon dioxide in the air. And I would say, well, the process that takes carbon dioxide out of the air is what? And you know, what process do plants do? And you sort of give hints. And they would say, well, photosynthesis, okay. So photosynthesis is taking carbon dioxide out of the air, great. And then what is it that eats plants? Or, you know, well, we have animals here now. How is that carbon going to get from the plants to the animals? And the students will say, well, obviously they eat them, great. So here we've got feeding that happens. And then when animals and plants die, we've got death and decay, what happens to them, or what organism in the soil is going to help break them down, microorganisms, etc. But what I found was that even though I thought that, and then obviously we talk about respiration. So what is the process in animals first that releases carbon dioxide back into the atmosphere? And if you've checked their prior knowledge on respiration, they should be able to tell you and say, well, actually, is it just animals that respire? Or is it all living things? And it's all living things, great. So plants have to do it as well. And in fact, microorganisms do too. And although this seems like a really straightforward link between the prior knowledge of photosynthesis, respiration, combustion I haven't done yet, but we would then add that in when we combustion of fossil fuels. What I still found that particularly my weaker students really struggled to remember this diagram and to talk about it and to recreate it and be able to write about it. And I thought, well, actually, I'm not sure that they understand why the carbon cycle is so important. I'm not sure that, although they might know these individual processes, I don't think that they get why the carbon cycle. So I changed up how I did it. And in fact, when I was checking their prior knowledge on respiration and photosynthesis and combustion first, I'd get them to write out the equations. So not get this the wrong way around. Respiration, glucose plus oxygen gives us carbon dioxide and water. And what I would do is I'd say, as part of the recap, I would get them to say, okay, well, where does that glucose come from? Where does that oxygen come from in particular? That's the one we're really interested in. Where does carbon dioxide, sorry, that's the one we're really interested in here. Where does the carbon dioxide go after respiration? And recap that, so it goes to the air. But I get them to annotate all of these. So the oxygen comes from the air, and glucose will come from your digested food. Great, and then I get them to do the same thing with photosynthesis. So again, you know, I'll do it quickly. So carbon dioxide and water gives us glucose plus oxygen, and then we've got it balanced. All right, now for each of these substances, either where do they come from or where do they go? So the carbon dioxide comes from the air. So I was building in the sort of making sure that they had the prior understanding that they need to really understand carbon cycle really explicitly written down in their books as much as anything else, and that they've verbalized it and they've really recalled every aspect of it. So this water is obviously from the soil. It could be used to release energy, stored as fats, oils, etc., etc. Starch, because we're going to talk about food and animals, and then the water the oxygen goes to the air. And then I did the same thing with combustion. I'll leave that one there for now. But so again here, we're starting to look at where the carbon dioxide in respiration is going to, where the carbon dioxide in photosynthesis is coming from, and importantly, this molecule here, glucose, because I then said to them, okay, well, what is it? So I want to get them to understand why the carbon cycle is important, why we need it. I said, okay, well, what is it that keeps us alive? Where do we get our energy from? So I started from us, from humans, aka animals, that students will be more familiar with, and they'll know that we get our energy from glucose because we've just discussed it when we've recapped respiration. I said, okay, so glucose is a really important, it's one example of a really important carbon compound. So in living organisms, we have a whole load of carbon compounds. And we'll focus on animals first because we are animals. So we have a whole load of carbon compounds in animals. One example being glucose. And particularly with foundation students, I wouldn't necessarily expect them to remember this, but I give them the formula to show them where that carbon is. Okay, well, where do we get our glucose from? Well, we get it from the food that we eat. So that will be either animals or plants. So when we eat plants, they also have carbon compounds, such as starches, which will be made up of glucose. And so when we eat the plants, we are digesting the carbon compounds that are in the plants and then using those digested compounds to make our own carbon compounds. Okay, right. So carbon compounds in plants, like glucose, also have carbon, but where did they get their glucose from? And you've just revised it, haven't you? Because you've just done photosynthesis here. So they should be able to tell you, well, they get it from photosynthesis. Okay, well, look really carefully at the equation for photosynthesis. There's carbon there. Where has this carbon come from? And it has to have come from one of the reactants. And the only reactant it can have come from is the carbon dioxide here. Great. So the carbon in the carbon compounds in the plants comes from carbon dioxide in the air. And they got that and carbon, and they're able to incorporate it into this glucose through photosynthesis. And then from there, you can then do the rest of it, and you can talk about death and decay, microorganisms, which also have carbon compounds. Okay, so it's the carbon compounds in the microorganisms as well. And at this point, you can go, well, hang on, if carbon dioxide in the air is being taken in by plants to form carbon in the carbon compounds there, and then it's going to the animals and then to microorganisms, that's essentially a one-way system. We're going to run out of carbon dioxide in the air eventually. So something has to be putting it back into the air. Well, let's have a look at the equations that we've just recapped. Which of those puts carbon dioxide back into the air? And obviously I'm going quite slowly if I've got a lower ability group, but your sharper kids, your higher ability students will be able to get that really quickly. And then you've completed your loop, haven't you? Because you've got respiration there. So by doing it again differently to how I traditionally taught it, by focusing on the importance of the carbon compounds and starting with humans and animals and where we get carbon compounds like glucose from, because they're familiar with that, it just seemed to make a lot more sense to the students. And the way that it was then constructed made a lot more sense to them. And I think that it was because I was starting with what was most familiar to them, rather than just starting with this cycle that's kind of abstract and links loads of different concepts together. Yes, that they do have prior knowledge of, but it's still quite difficult to get your head around why this happens. So instead of doing that, I started with just what they know, what's most familiar to them, animals themselves, where they get energy from, glucose being a carbon compound, and built it up from there. And also focused very much on why the carbon cycle is really important. So again, that was just a different way of sequencing that made a huge difference, I found, to those students. And the third type of sequencing in my explanations that I try to use as much as possible is sequencing that helps to really create links between things to help students really understand those links, but also then remember longer term. So it's going back to this idea of sequencing being the way that we combine different things in a particular order to help them remember. And so this is the example I want to show you. Circuit diagrams. Now, students tend to remember the first few circuit diagrams quite easily. So open and close switch, and the cell and battery and lamps, voltmeters, ammeters, because they're ones that they should be familiar with from primary school, actually, from Key Stage 2. And then we've really reinforced that at Key Stage 3. The ones that I found that my students really struggled to recall were things like the diode, the variable resistors, the thermistors, the LDRs, the LEDs. So I'm going to focus on the resistors. And what I've started doing, traditionally when we teach this topic, we'll do series and parallel circuits, and then what current is and what potential difference is, and then what resistance is, and then we'll do various other bits and resistance required practicals and things like that at GCSE. And then we'll go on to maybe thermistors and LDRs. But why not just teach all the different types of resistors in one go? And I'll explain to you why I think this helps. So what I did is I started to sequence it. I started to group. So I'm combining now all of the different resistors together and teach them at the same time so that I could do this. So this was now about trying to get them to recall those symbols long term, because they just couldn't remember them, or they confused them really, really easily. So they couldn't remember which one was the thermistor and which one was the LDR, and which one was the LED, etc., which one was the variable resistor. So I said, okay, we're going to look at all the different types of resistors. And this symbol here is a symbol for a resistor. And you know that because it's got a rectangle. So this is just your really standard symbol for resistor, and it's a resistor that doesn't change resistance. So we call it a fixed resistor. Okay, so there's your fixed resistor. It's got a rectangle. So anything, by the way, that has a rectangle in it is a type of resistor. Okay, so anything, any symbol that's got a rectangle in it like that is a type of resistor. So I'm creating links for them here. So I say, okay, so if I have this symbol, what's that? Well, it's a type of resistor, miss. Yes, it is. How do you know it's a type of resistor? Because it's got a rectangle. Excellent. Is it a fixed resistor though? No, it's not. How do you know it's not a fixed resistor? Because it's got that arrow going through it. Right. So we know it's a resistor, but it's not a fixed resistor. Okay, so it's got this arrow going through it. This is a type of resistor that you can change the resistance of. So you can vary its resistance. So we call it a variable resistor. And I think of that arrow as a speed dial. That's how I remember it. So think of your speed dial in your car, which changes, as the speed changes. So this speed dial or arrow indicates that the resistance can be changed. So that's my variable resistor. Okay, and it's got the speed dial arrow going through it. So what's this one then? Oh, well, that's another type of resistor, miss. Well, how do you know it's a type of resistor? Because it's got that rectangle in it. Great. So it's another type of resistor. Okay. And this extra little symbol there, I think of as a straw. Now, you can also draw it this way around. It doesn't matter because it's just the same symbol, just flipped over. So it's just like you flipped over your component. But I draw it this way because that reminds me of a straw. And as soon as I think straw, I think, hot and cold drinks, and heat and hot things, hot and cold, makes me think of thermal. What does thermal mean? Oh, it's to do with heat, miss. Okay, great. So this is a thermal resistor. And now if you prefer remembering it like this, I remember this as a hockey stick, which is played on ice. So again, there's very little thermal energy in ice, but you're back to the word thermal. So this is a thermal resistor, which depends on temperature. Okay, it depends on the amount of heat energy. But instead of calling it a thermal resistor, what people have done, what scientists have done, is they just squashed these two words together, and they have just created the term thermistor, but it is a thermal resistor, okay, which it depends on temperature. Great. So let's do one more. So here we've got this symbol. What is that? Isn't it another type of resistor, miss? Yes, it is. Of course it is. Why is it a type of resistor? How do you know? Because it's got that rectangle, right? And by this point, that link in their minds that every time there's a rectangle in that symbol, it's got to be a type of resistor is really well embedded now. And I say, okay, this is a type of resistor that doesn't depend on temperature like the thermistor did, but it depends on this. So these two arrows falling on the resistor actually represent light. So what is it that this resistor depends on? Well, it depends on light, miss. You just told us. Yeah, so it's a light dependent resistor, or LDR. Great. And then I'll cover it all up and I'll test them on it. But because the way that I've sequenced it has created these links for them, they're going to remember that now. And I found that this, I don't want to say foolproof, but it was much more effective teaching it this way to my students in terms of long-term retention than anything else, than any flashcards or trying to get them to quiz each other loads. Just explaining it like this in a way that just made sense to them meant that they remembered it. The beauty of this one as well, so 2 arrows representing light, is that after you've taught them about diode, you then have this symbol here, and I say, well, what are those two? So you've already talked about diode at this point. Well, what are those two arrows? Remember what these two arrows were here? Well, they were light. Okay, so what are these two? Well, they're light as well, miss. Great. But this time, is the light falling on the appliance or is it leaving the appliance? Well, it's leaving it. Okay, so the term that we use for that is emitting. So this is a light emitting diode, because it's emitting, because it's giving out the light. And you know it's light because it's this double arrow, just like we had with the LDR, and that is your LED. And then they go, oh yeah, I know what an LED is. But now they're going to remember that symbol because you've linked it, you've shown them the pattern of what these symbols actually mean. So again, that's about sequencing to create links to aid recall long term. Okay, so with sequencing explanations, teacher explanations, we need to go beyond merely just checking prior knowledge and understanding, because very often I think we assume that then if the students have got that prior understanding, then they're going to get what it is that you're explaining, whereas there is a bit of a gap there, and we need to make sure that we're also sequencing within that gap. And we do that by starting at the genuine beginning, by starting with what's concrete and observable if we can, by maybe starting with what's most familiar to the students, and making links really explicit in our sequencing, because essentially what you want is for there to be a bit of a narrative through the content, even at the level of your explanation. So we talk often about curricular narratives, you know, or narrative through a unit, but even at the very micro level of your explanation, we need some sort of flow to keep students with us. So what does this mean if we go now to the other end of the scale, to the curricular level? What does sequencing mean at that stage, at that level? Well, I think that the same principles apply, actually, that we need to start at the beginning. We need to start with what's concrete or observable, or start with what's most familiar to students, and then make those links really explicit throughout our sequencing. Now, I said at the beginning that we've been resequencing our Key Stage 3, which is a project that we're really excited about, actually, and I'm going to give a shout out now to three of my wonderful science director colleagues, Alison Chiverton, Alok Kanwar, and Adam Singleton. And this has been a bit of a project, actually, since January, and we're really excited about what we've achieved. So what we started with was actually looking at the Key Stage 2. And what we found when we looked at the science that was done at Key Stage 2 was that a lot of it was really concrete. It was stuff that students could observe, that they could get their hands on very often, and that they could experiment with. So it's not discovery learning, but it's definitely experiential learning, you know, and it was very hands-on, and not very abstract. And obviously a big part of that is because at that age, students really struggle with abstract concepts. They haven't developed that cognitive capacity yet. But I think the same is true very often with our year 7s, because our year 7s are only just come out of nursery. Sorry, I was thinking babies in my head. Our year 7s have only just come out of primary school, haven't they? So I think that particularly with year 7s, when we're starting our Key Stage 3, we need to try and follow the same sort of principles initially. So we then looked at our Key Stage 3, and we looked at the Key Stage 3 national curriculum, and we looked at how traditionally Key Stage 3 has been sequenced or been taught. And very often people start with biology as the first unit and start with cells as the first unit. Because we know that cells are the fundamental building blocks of all living things, right? And then you might go on to chemistry, and you'll learn about particles with your teacher of year 7's particles, because particles are fundamental of all chemistry. And then you might go on to physics, and it might be forces, you might do energy, depends, it can be a bit variable. And we had a massive conversation about why this was. And I have a bit of a theory, and it's not a very popular theory, I think. I don't know whether it's true, but this is just my thinking, because we were thinking about why is it that we always used to teach biology first and then chemistry and then physics. And I know that a lot of schools are changing that now, and I know that there's some wonderful blogs out there about Key Stage 3 sequencing that argue that maybe we shouldn't be doing it in this order. But we were trying to think, why is it that pretty much all schools for a very long time did biology first, then chemistry, then physics? And the only reason that I can think of, and it's horrifying, is because it's alphabetical. I'm more than, and I don't know whether this is true, I would be more than happy to have somebody who wrote the original Key Stage 3 national curriculum way back when to tell me, to contact me on Twitter, or just say, well, actually, that wasn't why we'd actually thought about the sequencing. But I can't think of another reason. It is alphabetical. And so I think that when it was written in the national curriculum, it was biology first and then chemistry and physics. And we always talk about them in that order. And the exams, GCSE exams are in that order: biology first, then chemistry, and then physics. And you just think, why? And I can't get out of my head that it's alphabetical. And it's a horrifying thought that the reason why we sequence topics the way we have was purely because it's alphabetical, rather than there was a genuine reason for sequencing it that way. So we talked a lot about this, and we read a lot of blogs on it, and so we thought, well, what are the first fundamental concepts that absolutely underpin everything in our subject? And when you look around you and you look at everything to do with science, everything is made of matter and energy, and the idea that they need to be conserved. You can't create them, you can't destroy them. And I think these two ideas, matter and energy, and their conservation, underpins basically the rest of science. So that's where we start. So we have a unit now in year 7. We have an introductory unit to science at secondary school, safety in the lab and equipment and what it looks like, etc., etc. And as part of that first unit, we're also going to assess, but through a sort of fun quiz, what it is that they do or don't remember from Key Stage 2, so that we're fully aware of what our starting point is. And we'll do our Bunsen burner license and an initial simple practical, heating water, finding the boiling point of water or something like that. But then our first Key Stage 3 unit proper is matter and energy. And we've combined these because actually, yes, technically matter is chemistry, although there's a huge overlap between that and physics, isn't there? And traditionally energy is a physics topic. And I'm sorry to all the physicists out there, but energy isn't the preserve of just physics, because it's really important in a lot of chemistry topics. It's really important in biology topics as well. From digestion and respiration through to food chains, etc. Students need this understanding of energy. So these two are fundamental to all of our other science topics. So that's where we start. Then we talked a lot about cells being, what should cells be the first biology topic. So we've already decided we're starting with the introductory unit first, and then matter and energy. And then we talked a lot about, well, traditionally we then go, when we do biology, we go into cells, right? And we do animal and plant cells, and we do subcellular structures. And one of the things that we'll do is we'll do cells, and then tissues and organs and organ systems. And so, a group of cells, a group of similar cells is a tissue, and a group of different tissues working together is your organ, and then a group of different organs working together to perform the same function, the same overall function, is your organ system. But we wanted to really try and stick to the principle of starting with things that are concrete and that students are more familiar with, and working down towards abstract. And I think that actually cells is a really abstract concept, because you can't look at your skin and see your cells. Students, it's really difficult to visualize, and we have wonderful diagrams that we show them. We get the students to draw them, and we'll get them to look at cells under the microscope. But students looking at cells on the microscope are very often really struggle to make out what's there, and they eventually make it out because we've shown them so many pictures, so many diagrams, and we'll point it out to them, and we'll tell them, well, there's a cell membrane in the nucleus that you can see, but you can't see anything else inside the cell. So I think cells is a really difficult place to start for our students. And if you think to the Key Stage 2 as well, they've already done stuff on organ systems. They've already learned about some of the major organ systems. So why don't we start with organ systems in year 7 as well, when we start biology? So we flip this over. We start with the organ systems and the organs in them, because students are already familiar with a lot of them. So we're starting from what students already know and what they're already comfortable with. They can list organs for you, and they might even be able to remember some of the organ systems and what they do from primary. It doesn't matter if they don't, but at least you're starting from a place of prior knowledge, of secure prior knowledge when you're talking about organs. And then we'll go down to tissues and to cells. So links much better to Key Stage 2 this way around, and we're starting with what students can observe, what's more concrete, down to what I think is more abstract when we're talking about cells. So if this is our starting point, what about cell structures and their functions then? So, we'd start with organ systems, organs, tissues, go down to cells. Okay, so surely once we're talking about cells, we can talk about subcellular structures and their functions. And this is where, we'll have diagrams like this, and we'll talk about all the different parts of the cell and what they do as well. But when we talk about things like mitochondria, and we define their function, we'll say, well, that's where respiration happens. And we'll talk about chloroplasts in plant cells, and that's where photosynthesis happens. Students haven't learned about respiration and photosynthesis yet, if this is your first introduction to biology in year 7. So you're saying, well, chloroplasts is where photosynthesis happens. Actually, photosynthesis, they might know from primary school, but certainly respiration, they won't know from primary school. Happy to be corrected, but I don't think that they do. So mitochondria is where respiration happens. That's how cells get their energy, but we'll learn about that later. And that was a bit of a light bulb moment for me when I thought about this. Was last year, I think. I'd read something about it, and I thought, well, every time you say to students, but don't worry about that, we'll learn about it later, essentially, they haven't already got that hook in their brains to attach that knowledge to. And so what you're giving them is actually an unconnected fact that you're expecting them to remember, and that's really hard. And this is why I think we get to the start of GCSE and we have to reteach this, because too many students don't remember the names of the structures and what their job is. Ribosomes being the site of protein synthesis, or where proteins are made, if we're going to change the language that we use for students, but they don't really have a very solid understanding of what proteins are yet. So actually, we've decided to leave cell structures and functions until year 8, and possibly quite controversial. And I think that we're lucky in that we had a bit of a blank slate, and we were allowed to suggest these what might be considered to be more radical changes. But I don't think that they're hugely radical, because to me they just make sense. So our first biology topic is actually just organ systems, and we do talk about cells a little bit, but this is the sequence that we've gone with. Introduction to major organ systems, which links really nicely to their key stage 2, and so we'll list all the major ones, and we'll give them diagrams of them, and we'll get them to label as many organs as they can, and they'll know quite a few of them already. We might have to fill some blanks, but that's fine. Then we'll introduce them briefly to tissues and to cells in terms of them being building blocks of the organisms. So these organs are actually made of tissues, and the tissues themselves are made of cells. So we're starting from the big picture and working down to the more microscopic, so macroscopic to microscopic. We then go into a few of the key organ systems. We've chosen to do digestive system first. Again, it's one that students are often more familiar with, then respiratory system, and then circulatory system. And the reason why we've done it in this order is because your digestive system is where you get your nutrients from, and obviously your food, which are then transported by the blood in your circulatory system. The respiratory system, one of the things that you'll get is oxygen into your system, which is then transported by the blood in your circulatory system. So it felt like, if we're thinking about that narrative and starting at the beginning, it felt like this was a nice way to do it. And then you've got your blood. Now you're in the circulatory system, and your blood is transporting all these substances around your body. Well, why does it do that? Well, it's obviously because your cells need this. So now we go back to cells, but remember, in that second point, we've introduced them to cells as being the fundamental building blocks of organisms. But all of these substances that your blood picks up and carries around, it's taking things to the cells and taking things away from the cells. So at this point, we do a simple introduction to respiration in cells. And then we go on to reproductive system and puberty, because we feel like that's obviously a really important topic for us to do with our year 7s in terms of PSHE as well, and their understanding of that. But this is unit 4 in our sequence. So we're not teaching this until after February half term, thereabouts, maybe starting just before February half term. So yes, we're introducing respiration, but we've already introduced the reactants that are required and how those get to the cells, so with our circulatory system. And before this unit, we actually do chemical reactions, simple chemical reactions. So unit 3 is simple chemical reactions. And we use, so we've already started to talk about reactants and products. So when we introduce respiration here, it is as a chemical reaction that happens in the cells. We don't go into organelles at this point. We don't need to say, that's what we've chosen to do, that respiration happens in the mitochondria, because by this point they've had quite a lot of information already. And as for me, I'm happy as long as they know that respiration is a chemical reaction that happens in cells. When we do organelles in year 8, then we can use that as an opportunity to recap respiration and then say, and you know what? That respiration that we learned about last year, that chemical reaction, happens inside this particular organelle. And the same with photosynthesis. So later on in the year 7 units, we learn about photosynthesis, but we don't talk about chloroplasts at that point in the plant cells. But when we then do plant cells in year 8, then we can actually put that photosynthesis, which they now have a good understanding of, into context in the chloroplasts. And again, same with specialized cells. We'll do a little bit about specialized cells, just in terms of there are lots of different cells, and particularly because in the reproductive system, they need to be able to talk a little bit about the egg cell and the sperm cell, don't they? But again, specialized cells, when we do in year 8, is an opportunity to revisit this and to really delve in much, much deeper. So this is what our year 7 curriculum map looks like now. And what we've done is really try to make the links between each of the units very, very clear, and why we've sequenced them in that order. And in terms of training up our staff and involving them in the curricular conversation, now that's the stage that we're at. We're very much now encouraging our teachers to articulate these links themselves. So as simple as taking this diagram and annotating all of those links. So obviously they've got all the content of each of those units, and they can look at them and look at what the links are. What is it that we've left out of the Key Stage 3 national curriculum? What is it that we've maybe added in? So for example, sustainability isn't part of the Key Stage 3 national curriculum, but we've chosen to include it, as I think many schools would. Why is that? So we're now at the stage of having all these curricular conversations, why, and talking about the why of our sequencing, so that hopefully, if all the teachers are really clear on that and they've been involved in those conversations as well, then when it comes to teaching, they're going to also be able to narrate that sequence to the students, and which ultimately is only going to help students, I think, embed their knowledge even more. So remember that it's the process of combining things in particular orders, not just putting them in particular order. We're starting at the beginning, starting with what's concrete and observable, starting with what's most familiar, making those links really explicit, because ultimately we want students to be able to hang this new knowledge on really, really solid hooks, which are themselves really securely attached to that plank, which is itself really securely attached to that wall. I mean, that metaphor could go on and on, couldn't it? Because these individual facts are difficult to remember. If we make links between them, but more importantly, if we manage to make really solid links to prior knowledge, I think that is the most important part of sequencing. And ultimately our aim is for our students to remember long term what they've learned in Key Stage 3 and then through to Key Stage 4 and beyond. And I will stop there. And I'm hoping Louise might come back at this point.
Nearly there.
Hiya.
Hello. Oh wow, fantastic. Thank you. That was brilliant.
Thanks.
Yeah, my mind is now just sort of thinking of all of those. Good night. Love you.
Good night.
Sorry. Good night.
No, it's fine.
Sorry. Can you close the door? Yes. Bombed right at the last minute. I thought, okay.
Excellent.
Yeah, I've made absolutely tons of notes and messaged my team that I'll be forwarding them the video and stuff straight away. I find it really interesting that thought process that you've gone through. I think especially at the end when you're saying, actually, why are we teaching things? Why do we it's like we fall into this trap, don't we, almost, of why are we teaching things in this particular order?
Because we always have.
Yeah. And it's the same when you hit that Key Stage 4, isn't it?
Mm-hmm. So,
and I know we talk about the kind of like you're sort of spiraling up, but are we really spiraling up, or are we kind of actually ad hoc?
And then maybe making big jumps when we shouldn't be making such big leaps sometimes as well. And yeah. So we've obviously done a lot of the Key Stage 3 work now. We're still fine-tuning our year 8 and writing that in detail, but in my head the next stage is, well, obviously you keep going, don't you?
Just seeing if anybody's got any questions at the moment. Yeah, the other thing as well, because I'm going to watch this, I'm going to watch it back again, but when you were going through the carbon cycle as well, and actually because I've just done undoing exothermic reactions, and you do, and it's just like, it's one of those things, it's like when you go through the papers and you're looking at sort of